Okay, before we move on to fluid kinematics, we'll do a little bit of a math recap. This is by no means comprehensive, but if there are aspects of the following couple of videos that you do not understand, please read up on it. There's much more in the textbook, and also might be good to revisit your calculus classes, etc. So first, let's talk briefly about the vector dot and cross products. The dot products, also sometimes referred to as the scalar product. So if you have two vectors, u and v, the dot product describes the product of one vector times the projection of the other vector in the direction of the first vector. So let's call this distance here a, and then u dot v is the magnitude of u times the distance a, and if this angle here is theta, then you'll see that a is just v cos theta. And similarly, if you project u onto v, you have a distance b here, and the dot product of v dot u is magnitude of v times b, which is just v u cos theta. So that means that the dot product is symmetric, i.e. u dot v is the same as v dot u. Now, two special cases. If these two vectors u and v are collinear, so if you have u and v pointing in the same direction, then, i.e. the case theta equals 0, then obviously u dot v is just the product of the magnitudes. And if these two vectors are orthogonal, then u dot v is 0. Finally, in index notation, you would write u dot v, well, it's simply u1 v1 plus u2 v2 plus u3 v3, where u is u1, u2, u3. And so, just to remind you, we can write this as the sum over I from 1 to 3, and then using the Einstein summation convention, you can actually just write this as ui vi. So that is the dot product in index notation. Now, let's talk about the cross product. The cross product is defined for a system of three vectors, and so if you have u and v again in a plane, two non-collinear vectors always define a plane. Then you have a third direction that is orthogonal to that plane, and this vector w is defined as the cross product of u and v. So this cross product is defined by four properties. First, w is perpendicular to the plane defined by u and v. Second, the length of the vector w is u v sine theta. It is antisymmetric, so u cross v is the same as minus v cross u. So v cross u is minus w. And then fourth, if you have a orthonormal basis defined by three basis vectors e1, e2, e3, the cross product is defined to say that e1 cross e2 is equal to e3. So the system is always defined to be right-handed. So if you go from E1 to E2, and then the direction of E3 is upward. And so if we have defined 1, 2, 3, and 4, then you can show that the cross product U cross V is just given by the determinant of following matrix, which is simply U2 V3 minus so that's the cross product of two vectors. And again, we can write this very succinctly in index notation. So each component can be written as follows. Say the kth component of U cross V can be written as WK is, well, this is actually the vector W dotted with the basis vector in the k direction. So k can be 1, 2, or 3. Yeah, so if we have a random vector W and a basis 1, 2, 3, then W can be decomposed into components along the three bases directions, 1, 2, 3, and say W1 in that case is just the dot product of W with E1. Yeah, so this is W1, this vector here, U2 and W3. So for the general kth component, we compute the dot product with EK, and so this is U cross V dotted with EK, and that can be very succinctly written using the alternating tensor epsilon Kij Ui Vj in index notation, and this is the alternating tensor, and the symbol epsilon here is referred to as the Levi-Civita symbol. Now, what does epsilon Kij look like? What sort of tensor is this? Well, it's a third order tensor, IJK, third order tensor. So it's essentially three 3x3 matrices, and it has the following specific properties. Epsilon IJK is equal to 1 if IJK is an even, or also known cyclic permutation of 1, 2, 3. So epsilon 1, 2, 3 is equal to epsilon 3, 1, 2 equal to epsilon 2, 3, 1, and that's equal to 1. Now epsilon IJK is equal to minus 1 if IJK is an odd permutation, and epsilon IJK is 0 if two or more subscripts are the same. So if I tried a graphic representation of this tensor epsilon, it would look like this. JK, this would be 0, 0, 0, 1, 0, minus 1, 0. So for our vector W, let's say W1, for example, is W dotted with E1, which is U cross V dotted with E1. And if we look back at our vector here, if I dot the left-hand side, if I dot each term on the right-hand side with E1, then you quickly see that these two terms obviously go to 0. This goes to 1. And we are just left with U2 V3 minus U3 V2. That's W1. And so we can add the Levi-Civita in here, we need the free index on the Levi-Civita to be 1 and the dummy variables to be 2 and 3. So we have epsilon 1, 2, 3, u2, v3, minus 1. So when does this become minus 1? It's when we have plus epsilon 1, 3, 2, u3, v2, which in summation notation is simply epsilon 1 ij times ui vj.